Here are the sample problems for Math 117, class number 11, and I've decided I'm going to do number 2 before number 1 because number 1 actually uses the result that I'm going to prove here in number 2. So x is a random variable and it's not necessarily bounded, but I'm putting on the restriction that it can only take on non-negative integer values, and I'm defining a sub k to be the event that the value of x is greater than k. So a sub 5, for example, is the event that the value is greater than 5, i.e. 6, 7, or so on. So here's a very clever way of rewriting x. First term in x is the indicator function for a0. And that will have the value 1 as long as the random variable is larger than 0 for 1, 2, 3, 4, and so on. And then I add on to that the indicator function for a1. That will be equal to 1 if x is greater than 1. I add on the indicator function for a2, adding an extra 1 if x is greater than 2, and so on. So, for example, if the value of the random variable is 3, this will contribute 1, this will contribute 1, this will contribute 1, but the indicator function for a3 and subsequent will contribute. So, now I'll calculate the expectation of x by exploiting the fact that the expectation of the sum is the sum of the expectations. So this is equal to the sum for k equals 0 to infinity of the expectation of the indicator function for event a sub k. But the expectation of an indicator function is just the probability of the relevant event. So that is equal to the sum from k equals 0 to infinity of the probability of the event a sub k. And this is the tail sum theorem. Now, the way we make unbounded random variables out of bounded random variables is by making out of x the random variable x super m, and this is redefined so that the probability that x is greater than m is equal to 0. In other words, if the value of x would be greater than m, we change that value to m. And now, if we're considering the specific random variable that has the geometric distribution property, that is, the probability that you get failure on the kth attempt is q, then the probability that x is greater than k, that we have to go beyond k trials to get success, is q to the k, but only if k is less than or equal to m. We're guaranteed success on the mth try. So, I can calculate the expectation of x super m very easily. I'm now summing from 0 only to m minus 1 because the probability that x is greater than m has been made equal to 0. This is a well-known sum. It's 1 minus q to the m over 1 minus q, or denoting the probability of success by p, it's 1 over p times 1 minus q to the m. And finally, taking the limit, the expectation of the unbounded random variable x is just the limit of this as m approaches infinity, and the limit of 1 over p times 1 minus q to the m is equal to 1 over p. A very well-known result. And if you say, couldn't you just have done the sum all the way to infinity in the first place? The answer is yes. I'm just trying to be careful about it because I have done it in such a way that the probabilities always sum to 1. If I do the usual sum to infinity by saying replace all the terms beyond the mth term by 0, then my probabilities don't sum to 1. Okay, so that's problem 2, and now I can use that to solve problem 1. I can even fit it on the same page. So, here's the plot. Someone graduates from college and says, before I get married, I want to do a job that makes me happy, a job that makes me famous, and a job that makes me rich. And a randomly chosen job has a probability of 1/3 of making you happy, making you famous, or making you rich. This happens independently for one job to another. And the question is, what's the expected number of jobs required before our college graduate is ready to get married because he's happy, famous, and rich? Well, for the first job, the probability of acquiring one of these attributes is 1, and the expected number of jobs is also equal to 1. He's guaranteed to pick up one of the attributes. For the second job, there's one chance in 3 that the job confers the attribute he's already got. That is, the first job made him happy, and all the second job does is to continue to make him happy. The probability of picking up a new attribute is 2/3, and for that, 1 over p is 3/2. And now for the third job, he's got 2 of the 3 attributes. He might, for example, be happy and famous, but not yet rich. The probability of picking up the third attribute is 1/3, and so 1 over p is equal to 3, and the expected total number is 1 for the first attribute, plus 3/2 for the second attribute, plus 3 for the third attribute, or 5.5 jobs. You'll see, I believe, when you do the homework, that there are significantly more complicated variants of this problem. Okay, let's move on to number 3. This is a very famous result involving the Poisson distribution. So we're carrying out n trials. N has to be larger than some positive real number alpha that we've chosen in advance. And for each of these trials, the probability of success is alpha over n. So for example, we might choose alpha equals 3 and n equals 100. That means the probability of success on each individual trial is 0.03. The number of successes is clearly a random variable, and although it's already in the statement of the problem, I'm going to write this out, but in a slightly different way. So the probability of this random variable, the probability for it to have the value of k successes is the following. The first term in our binomial distribution is n choose k, or n factorial over n minus k factorial times k factorial. That's the number of ways of selecting the k successes among the n trials. And when I divide n by n factorial by n minus k factorial, of course I get n times n minus 1 times n minus 2, and the last factor will be n minus k plus 1. I have an alpha over n to the k, so I will write out the alpha to the k, but I will break my n to the kth power into n individual, k individual factors of n. I also have in the denominator a k factorial, and then I've got the probability of a failure raised to the n minus kth power because I have n minus k failures. And I'm going to split that up into two factors, 1 minus alpha over n to the n, and the other 1 minus alpha over n to the minus k. K is fixed, and I'm going to let n approach infinity. Okay, what have we got? Well, here's a nifty rewrite. N over n is 1. N minus 1 over n is 1 minus 1 over n. N minus k plus 1 over n is 1 minus k minus 1 over n. And then I also have in the denominator k factors of 1 minus alpha over n. K is fixed, alpha is fixed, so for this, the limit as n approaches infinity is 1. I've got alpha to the k over k factorial. That doesn't involve n at all. And what's left? This one, the limit is, as I trust you know, I think we did this in the first class, e to the minus alpha. So, the limit as n approaches infinity of the probability of the event, k successes, is just e to the minus alpha times alpha to the k over k factorial, and that's the mass function for the Poisson distribution. And problem 4 is a simple application of this. The mythical Nigerian lawyer is going to send you in the next 24 hours 48 spam emails explaining how he can help you claim a lost fortune if you just provide him with a little upfront money. He's not mailing these directly, though. He's sending them out by a spam bot, and the probability for any interval of length t hours that a specific email will arrive is t over 24. In particular, the probability that an individual email will arrive in a specific 1 hour period is 1/24. So it's easy to work out the exact probability that precisely 2 of the emails arrive between 9 and 10 a.m. There are 48 choose 2 ways of selecting 2 specific emails out of the 48. For each of those cases, the probability that one of those emails arrives between 9 and 10 a.m. is 1/24. For two of them, we have to square it. There remain 46 other emails. And for those, I have to raise 23/24 to the 46th power. And when I worked that out on my calculator, I got 0.276. However, this is the case in which the binomial distribution is nicely approximated by a Poisson distribution. So I can say I've got a Poisson distribution with parameter alpha, and the probability of getting precisely 2 emails according to the Poisson distribution is e to the minus 2, that's my e to the minus alpha from above, times 2 squared over 2 factorial. E to the minus 2 is 0.135. 2 squared over 2 factorial is 2, and I get 0.270. Pretty good approximation to 0.276. So anytime you're dealing with a binomial distribution with a large number of trials and you want to know the probability of a rather small number of successes, you can save yourself a lot of computational effort by approximating the binomial distribution by a Poisson distribution. Hey, that was easy. No messy proofs this week. I'm done.